Hey there everyone. In this video we are going to be looking at continuous random variables and how to compute their probabilities. Continuous random variables are distinguished from discrete random variables. Alright, so let's just take a look at that and see how it all works. We're going to first we're going to review what it meant to be discrete, and then we're going to talk about what the difference is between discrete and continuous. We're going to talk about the probability density curve, or the probability distribution function. It's the same thing. And we'll do an example of a continuous distribution and compute some probabilities. Okay, so let's take a look. So let's just review what it means for a random variable to be discrete. A random variable is discrete if you consider all of its possible values, not just the ones maybe you measured, but all possible values that it could possibly have. If you can list those, then the random variable is discrete. So an example of a discrete random variable is shoe sizes. The sizes can be decimals, right? But there's few enough of them that I can list them all because they come in halves, right? 6.5, 7, 7.5, 8, 8.5, 9. I can just write them all possible values. I can just put them into a list. And when I write down the associated probabilities, I have the probability distribution, and I can display that as a table, as we see over here, or I can display it as a picture, as a bar graph over here. Both those are giving us the same information, right? And so some features here are that the probability is the height of the bar in the bar graph. The probability for a discrete random variable is the height of the bar in the bar graph. Remember that because that's going to be distinguished when we get to continuous random variables. So keep that in mind. How do you get to a continuous random variable? Well, here's an example where we are going to look at, say, heights in centimeters of a group of randomly selected adults. Okay, and so what I'm going to do is I'm going to group those heights into intervals. Okay, so first interval I'm looking at is 150 to 155, 155 to 160, then 160 to 165, etc. So I've grouped the heights into these intervals. And I'm just looking at the number of adults in these intervals. And so what I've done is I've discretized the possible heights. I've grouped them into intervals. The intervals themselves are finite in number. There's only finitely many intervals, so they are by definition discrete. So this is what a discrete distribution of those intervals of heights would look like. Now, that was because I had a relatively small sample size, so it made sense to look at relatively large intervals just so I could get a decent number of people in each interval. Now, if I take a larger sample size, if I take more adults, I can get away with making the intervals smaller because now I'm not guaranteed, but it's more likely that even in a small interval, I'll have a reasonable number of adults, so I can draw a bar of a reasonable height. Right? If I took a bar as too small over here, chances are I may not even have any adults with heights in that range because I just have too few adults to deal with. So I might have a lot of bars that have height 0, so that wouldn't have really worked here. But in this situation, when I have more adults, if I have a sample size of, say, 100 adults, I'm allowed to make the bars smaller, and I get a nice histogram. Now, this is the same picture we had before for 100. Now let's look at if we sampled 1,000 adults. Well, now I can get away with making the bars even smaller. Even very, very, very tiny intervals will have a reasonable number of adults with heights in those intervals. But again, this is discrete because I have a finite number of intervals that I'm looking at. And if I go to 10,000, a sample of size 10,000, well, now I can make my intervals really, really, really teeny, and I still have a reasonable number of adults in those intervals, right? So I can make a meaningful histogram that way, provided my sample size is large enough. Now, what we see happening here is that as I let the sample size get bigger and bigger, I can see that this distribution is beginning to approximate a smooth curve. Or another way to say it is that distribution is approximated by a smooth curve. Now when I draw that curve, we've lost the intervals, right? They're no longer here. And we kind of have to do that. The set of all possible heights, if I'm not grouping them into intervals, that's not discrete. They are too numerous to list. If you think about it, if I was to try to list all possible heights, maybe 161.345 centimeters, then 161.349 centimeters, then 100, I try to list them. Well, somebody could come by and say, well, you missed, what about a height that's between those two? And you go, oh yeah, I missed that one. But that's always going to happen. If you ever try to list them, you'll always skip over one that was between two. So there's too many to list. The set of all possible heights, there are too many to list. And that's what it means to be a continuous random variable. A random variable is continuous if it's not discrete. And that means that the possible values are too numerous to be listed. And here's another example of a continuous random variable. Before we looked at foot sizes, that was discrete, but here we're looking at foot lengths. And we're measuring them down to fractions of an inch, all right? So if I go to fractions of an inch, there's infinitely many possible values that it can have. But even more than that, just being infinite isn't enough to say it's continuous, but they are too numerous, too densely distributed to list them all. And so that makes it a continuous. If we look at lengths instead of sizes, we look at lengths, these are continuously distributed. It's a continuous random variable. And that means that the distribution is represented by a curve. This is called the probability density curve, or often it's called the probability distribution function. Probability distribution function, and sometimes it's abbreviated PDF. Right? That's what we're getting here. Now, there's some important things to note about this. The total area under any probability density curve is equal to 1. Now, that should not be a surprise to you, maybe, because it shouldn't be too unfamiliar, because when we had discrete distributions, the total, if we add up all the heights of these bars, we're adding up all the probabilities, add up all these probabilities, you get 1. So it makes sense that we'd have something like that again. But in this case, it's the area under the curve, right? And if you think about it, I can't really use heights. I can't add up all the possible heights. There's an infinite number of heights here. I would get infinity, right? So that's not going to work. So we're using areas instead. And the probabilities are given by areas under the curve. So instead of, in the discrete case, what we did is to find the probability, we looked at the height of the bar. What we're doing now is we're looking at the area under the curve. Not the height of the curve, the area under the curve. So if I want to compute the probability that x is less than 9, I will find the area under this curve for all values less than 9. So this wedge shape here would be the probability. If I wanted to know the probability of a length being between 10 and 12, I'll find the area of this region here between 10 and 12 below the curve. Now, another important thing to consider, the probability of any particular value is 0. Well, that should make sense to you, because if probabilities are given by areas now, well, if I'm just talking about a particular value, x equals 12, well, that's an infinitely thin line. Well, the area of an infinitely thin line is 0. You know, the area of a rectangle is width times height. But a line has width 0, so its area is 0. So that means the probability that x equals any number is 0. Contrast that to the case we had before. If I rewind here, that was not the case for a discrete random variable. If I want to know the probability that x is equal to 9, I just take the height of this bar if the variable is discrete, and that's the probability. But in this case, That's not the case. The height of the curve is not the probability. It's the area of this line, and the area is 0. So make sure you realize that very important distinction between discrete random variables and continuous random variables. Because we're doing areas, the probability is not the height of the curve. It's the area, and that means that the probability that x equals something has to be 0. Let's look at an example. Here we have a probability distribution function, and it is comprised of linear line segments here. Compute the following probabilities. Okay, the first one is the probability that x is greater than 3. Well, what I'm going to do is I'm going to look over here and think about all the x's that are greater than 3. That's all these. And I'm going to find the area under this curve corresponding to that. Well, there it is. Right? It's the area of this triangle. Now, how do I compute the area of a triangle? Well, you know from geometry that the area of a triangle is equal to 1/2 base times height. So we can use that to get our answer. Okay, so let's do that. What's the base of this triangle? Well, it's 1, 2, 3, 4. It's 4 long. So and what's the height? The height is, well, it says over here on the y-axis, it says it's 1/6. So this is going to give me my probability. It looks like it's 4 out of 12. If I want to simplify that fraction, reduce it to lowest terms, I would get 1/3. Okay? All right, let's go to the next one. The probability that x is less than or equal to 0. Well, here we are. To be less than or equal to 0 means we're over here. And so we're computing the area of this triangle. Well, how do I get that? Well, it's going to be 1/2 times the base. Well, the base, how wide is this base? It's 2. And what's the height? Again, it's 1/6. So what am I getting here? I'm getting 2 over 12, or if I reduce that to lowest terms, 1/6. So the probability is 1/6. What about the probability that x is between 0 and 3? Well, I'm going from 0 to 3 here. So it's this area. It's the area of this rectangle. Right? So if I want this area, if I want this probability, I'm going to find the area of a rectangle. Well, this was the area of a triangle, AT, and the area of, let's use a new part of my paper here. The area of a rectangle, AR, how do you compute that? Well, that's just base times height. By the way, the reason that was you should know from geometry, the reason that a triangle is 1/2 base times height is because a triangle is exactly 1/2 of a rectangle. Right? Cut the rectangle in half, down diagonally, you get the triangle. That's why there's a half there. Well, if you do the rectangle, you don't have the half. Right? That makes perfect sense. So the probability that x is between 0 and 3 is the base, that's 3, times the height, that's 1/6. So that's 3/6. Or if you reduce that to lowest terms, it's 1/2. 1/2 of the area is in that rectangle. Right? All right, and the probability that x is between 1 and 2. Okay, well, to be between 1 and 2 means we're in here, right? So it's the area of this rectangle. What's the area of that rectangle? Well, it's base times height. Well, the base is just 1. It's 1 unit long. And the height, again, is 1/6. So the probability is 1/6. Now, you may have noticed something strange here. Did these or equal to's matter? If I had had this be less than instead of less than or equal to, would it make a difference? Well, if you think about it, the only difference is that if I have an or equal to symbol that means I'm including 1. But the probability that it equals 1 is the area of that line, which is 0, right? So the probability that x equals 1, if I ask this, what's the probability of x equals 1? We talked about this before, it's equal to 0. So what this is telling us is that or equal to symbol doesn't even matter. When you have a continuous random variable, the difference between less than and less than or equal to is nil. There is no difference. Now that's very different for a discrete random variable. For a discrete random variable, it made a big difference. You were either counting that value or you weren't, depending on whether this was less than or equal to versus less than. But for a continuous random variable, that or equal to part doesn't even matter. So that's kind of a nice aspect of this. The bad aspect of all this is that we have to compute areas, so it's maybe a little bit more involved getting our answers, especially if this was a smooth curve. Right? If this is a smooth curve, then computing the areas under there is going to be maybe a bit of a challenge. And so what we're going to need to do is we're going to need to use, in the old days they used tables that somebody had pre-computed for given curves, how to find the areas. Nowadays we can use computers. Or you can take a calculus class and learn how to compute areas under curves using integrals in calculus. All right? But that's it for today. Just wanted to share with you probabilities from continuous random variables. Okay? So I'll catch you in the next video.